All right, hi everyone. I'm Thierry. I'm currently an intern at Facebook, and I've been working the last month on Memoro, a heap memory profiler based on the LLVM infrastructure. And so oftentimes when I say that I'm working on a heap profiler, the question I get is like, why another one? So let's start with a quick example. We have here a function that takes a map, a bunch of keys, and return the value associated with those keys. So we create an array for our values, we reserve some memory to avoid unnecessary allocation, and then we loop on each and every keys, and we push them in the result array before returning it. But these codes contain like a bug. So raise your hand if you've seen where the bug is. Okay, let me give you a hint. This bug was costing 40 gigabytes of memory for every instance it was running on. This is a lot of wasted memory. Does that help you find where the bug is? Not really? Okay, I will come back to that. So, no, the thing is, we were just reserving the wrong amount of memory. And this is the kind of bug that typical heap profiler can't help you catch. The reason is that they keep track of how your program allocates memory, but they don't keep track of how the program uses the memory. And this is where Memoro comes in and is now able to give you both informations. So Memoro is based on the LLVM infrastructure. The LLVM allows us to manipulate the IR and to modify the behavior of your code without you having to change anything in your source code. And then we rely extensively on the sanitizer infrastructure. The reason is that this allows us to, for instance, collect stack traces, do symbolization, or even handle allocations. And all of this is already provided by the sanitizer infrastructure. And this allows us to really focus on just collecting data and displaying them in a meaningful way, and really giving insight to the user on what is going wrong on his application. So this is today's topic. I want to start with a quick overview of exactly how Memoro operates. So taking your source code, you don't have to modify anything. You just have to compile, and we have our instrumentation path that will instrument every load and store, instrument every intrinsic, and also along collect the data types of the allocation you do. And this allows us afterwards to provide you filtering capability so you can see which allocation your types are doing. And all you have to do is just add fsanitize equal Memoro. Then you start running your program, and we will intercept every allocation, every free. We'll also intercept every load and store. This is one of the most costly operations, but we'll come back to it. And we'll also intercept syscall to reduce the cone of shadow you might have in your application. And all of this data is collected and then dumped into a file that you can feed to the Visualiser, which is an Electron app. And the Visualiser will start doing some computation on your data, will attribute scores on different metrics. So for instance, if your program is allocating a lot of memory but only using part of it, the Visualiser is able to strike that. Or if you're doing a lot of short-lived allocation, this is also something that the Visualiser can highlight for you. And this is on an overview of how Memoro works. So let's start talking about the runtime overhead, because we're instrumenting each and every load and store. This is something quite costly. And to be honest, Memoro was primarily developed at my school, so it was mostly targeting research projects. And the challenge was to make it run on Facebook infrastructure. So we're talking about services that are running thousands of threads at the same time, and this is not something that Memoro was designed for. And the first time we were able to compile one of Facebook services and run it, we had 1,000x overhead introduced by Memoro runtime. And we had to work hard to reduce that number. So we started with something quite easy. First thing we introduced is runtime sampling. So we have all our load and store instrumented, and simply during runtime, when we have our callback in the runtime library that do the interception and like update the data according to the interception, what we do is simply increment a sample counter, and every time the sample counter is equal to the access sampling rate, we actually update the data with the sample. Otherwise, we just discard it and return immediately. This now offers some drawbacks. You have to choose between having high overhead, but high quality data, or low overhead, but this does reduces the quality of the data collected. But this is something that the user can choose now. And we also had to be careful about the sample count, sample counter, because we want to be able to cheaply discard those accesses. And to do so, we had to be careful because we were previously using a global variable. And since we are on heavily multi-threaded applications, this was causing a lot of cache line contention. So we had to make sure that those were thread locals to reduce the issue. But now we need to let the user define those different parameters. And so what we do is simply the same way ASAN does it. Like we provide you options on the command line, so you can set those different options through the environment variables. But we also provide you a public API. So that way, if you have, for instance, in your application, you have a warm-up phase, and you're not really interested in what the warm-up phase does. You really want to know what is happening in your program during the core of its work. So what you can do is simply disable Memoro at the startup, and once you reach the code you're really interested in, you can you can use the public API to turn it on and start collecting the data that are meaningful to you. Okay, so for now, we've came up with some tricks to reduce the overhead on Memoro, but we haven't really investigated what is the core problem we were having. So let's start to dive in and collect some metrics. And doing so, the first thing that struck me is how much time we were spending depending on the address type. So we were spending an awful lot of time on non-heap addresses. And remember, Memoro is a heap profiler, so why are we spending that much time on the non-heap addresses? Do you have an idea of exactly this not heap section is? Exactly, stack. So let's dive into the way the sanitizer infrastructure provided you allocators. So this is the root of our problem. So the sanitizer infrastructure provides us with an allocator to allocate on your behalf memory for your program. And the way it works is that it's split in two parts. You have the primary allocator, which is like the fast path. This is a common design in allocators. You have like a fast path and a slower path. And the primary allocators is the fast path, so it pre-allocates a very large region of memory, split it in different size region, and then it really is easy for it to return you some memory on your request. And if you're requesting too much memory, what will happen is that we will then query the secondary allocator. And the secondary one, what it does, simply does an mmap for your allocation, register the allocation in a vector to remember it, and return you the address. And the problem is that we are using this global vector to keep track of all the large allocation. And to prevent concurrent access to it and a race condition, we need to take a lock around this secondary allocator. So what is really happening is that what we have is that the allocators only knows about the heap addresses of your program. And the thing is, every time you give it a stack address, we need to go through everything in every allocation of your program. This is like a process of elimination. We have to ask the primary allocator, hey, do you know the stack addresses? No, I do not. Hey, secondary allocator, could you please take a lock around this vector and tell me, and iterate on each and every allocation and tell me if you know this address? No, I do not. So imagine now having like thousands of threads doing stack addresses at the same time, like fighting on that lock, trying to discard those stack addresses. This is the reason why we're spending so much time just discarding those stack addresses. So the fix we were able to come up with is that we implemented a runtime filter. The way we do it is simply every time a new thread starts, we store the top of the stack and we remember it for later. And then every time the instrumentation gets called, we get the current stack bottom. This is really easy. It's just reading the RSP register. And then it becomes really easy to just check our address if it belongs to the stack or not. And if it doesn't, we can then forward the request to the allocators. And the allocators will then return us the metadata related to the chunk being accessed. And we can then update that with the data of the access. And doing so allowed us to reduce the time spent on the heap. So we were able to reduce it from spending 99% of our time just discarding those addresses to only like spending 2% of the previous time doing everything. This was a great improvement, and this allowed us to reduce the Memoro runtime overhead from 1000x to only 5x. So now that we have reduced the overhead, we are now able to run Memoro on Facebook infrastructure. And we are able to run it on a service, collect a fairly big amount of data, and then we start to feed the data into the visualizer, and we encounter new problems. So the visualizer is an Electron app. So Electrons is like a web browser. That it's like an application. It appears like a system application. It appears like an application on your system, but it's just a web browser, and it allows you to really easily create web UI. And the way it works is that Memoro have a C++ module that will do all the loading the profile and doing the scoring on it, and then it will feed the data to the web UI to be displayed. And when you have 100,000 stake traces and 1 billion allocation, this is a lot of data to go through, and the web UI just can't deal with that amount of data. One of the big problems we had is simply the sheer amount of stack traces being displayed. So this is one of the flame graphs that Memoro can display you. And so on the x-axis, you have the impact of that stack frame. So for instance, if you select allocation size, the larger that allocation point, the larger amount of memory that allocation point did, the wider it will be in the flame graph. And on the y-axis, you have the different frames. And this is one of the results we had on one of our servers. We have a lot of those white spikes that are just noise and contain no relevant information for us. And this prevented the UI to be interactive. Like every time you would move the mouse or click on something, it would take like 5 minutes to just register your actions. So what we came up with is we noticed that only a few allocations were really allocation point, only a few stack traces were really having a meaningful impact. And so we have that long tail that is not really meaningful and just wasting pixels on our graph. So what we decided is simply to trunk that out, truncate everything out, and hide the data. And this is the result we have right now. This allowed us to keep the interface interactive. And what we would hope in the future is that you can click on those hide nodes and simply dive in. So every time you click on one of those hidden nodes, it would show you the data contained in that hidden nodes. But for now, it allows you to really focus on the most meaningful and most impactful traces. And yeah. And another problem we were encountering is that those small traces, they still contain some information in it. And I'm talking about the death by 1,000 cuts problem. So here we have two functions, foo and bar. And foo in orange have a big impact. It's really easy to read it. And bar has the same impact, but since you can have multiple paths leading to this, the call of the function bar is scattered all over the place, and you can't really see the impact it has. And the reason is coming from the way we built those stack traces. So we will build them from the bottom up, so starting with the main, adding the different function until you reach the bar function. And this builds some kind of trees with the main as your trunk and the bar function as your leaf. And the problem is if all those different paths get reflected in the graph and dilute the information. And so one solution to still highlight the impact of bar would be simply to build the stack trace in the reverse order. So keeping the same way, building the stack tree the same way, but simply instead of starting from the bottom of the stack frame, you start from the top, just reversing the order of the build. And doing so, it would give you this kind of result. And it becomes really easy to see the impact of foo and the impact of bar individually. And you could see, still have all the information of the stack and which function are calling bar that often. So you would get all the information, but in a more easy and approachable way. All right. And doing that, we were able to run Memoro on the Facebook infrastructure and collect some great data. And going through all the data, we were able to highlight the bug we were having previously about the large memory allocation. And so I won't have time for a demo. I think I'm a little bit too short. So I'm going to keep going. There's still some open challenges. I have time? Yeah. I'll look if I have time at the end. I want to be safe. Still have some open problem. So what happens is at the end of the program, when it shutdowns, typically when your program shutdowns, it calls our callback at exit, and we can start collecting the remaining allocations. We can start symbolizing the data collected and dump the file that you can then feed to the visualizer. The problem is that at Facebook, services don't really exit cleanly. They just crash and burn. And we don't really need to have them exiting cleanly because they're not supposed to ever stop. So this was never a problem we really focused on. But the result is that we don't get any data out of our services. And the trick we came up with to fix that is simply attach a debugger to the service when we want to collect the data and manually call the @exit function. So sure, we get the data out. It works, but it's really not that good. What we'll be looking for is maybe use a signal to start dumping the data. Or even better would be to have some kind of ring buffer and continuously write the data. I'm not aware if the sanitizer infrastructure provide any of those toolings, but this is really something that would help. Sanitizer usually don't really collect data that long to dump at the end, so I don't know if they have that kind of tooling. The other problem we are encountering is the previous problem regarding stack. We tried to do some compile time analysis to discard the stack addresses. And what happened is that we have our load and store. And we used getUnderlyingObject to walk up the SSA graph. And if we, at some point, we find out an allocate instruction, we would simply discard the instrumentation. But what we discovered is that playing with a little bit of the depth, it flattened out really quickly. And we still have like 50% of all our load and store that are targeting the stack, even with a depth of 8. So one of the reasons we think we have this problem is when you have two functions, and like foo is calling bar with some of its stack parameter, well, get underlying object is not able to bridge the gap, and we would need to come up with some better like interprocedural analysis to be able to have this information. So this is also something we're hoping to come around and find some improvement about it. And all right, that's all I have for today. So if I still have time, I can try and do a demo. Okay, so this is the interface of the visualizer. By default, it shows you the global view with the flame graph. And we can see here it's sorted by allocations. So it's really the wider the frame, the wider the higher number of allocation it did. We can change that, for instance, for the amount of memory it allocated. We can see how the memory evolves through time. We can even, if we want, zoom at some point in time. So this is the state of our memory at this point in time, and then later on, the program is doing something else, so we have different profile. And we can then dive on the detail view, and same thing, like for instance, sorting by allocation. We can have information about this allocation, detailed information about this allocation point. So here what we see is each and every individual allocation. So we have a lot of very short-lived allocation. And on the far right, you can see the different inference that Memoro was able to do on the data. So for instance, it's really highlighting that this chunk is has a high amount of very short-lived lifetime memory allocation and very low access coverage. So we're just wasting time in the allocator, doing very small allocations, and not even really using them. And yeah, we can see also the impact by amount of memory. And yeah. Oh, and you can do some filtering if you want on some precise stack traces if you want to. That's depending on what you want to know in your program. Okay, that's about it for me. Thank you for your attention, and if you're interested into running Memoro, you can go on this address to see the project. I'll be very pleased if you have any question. You can send me or need some assistance with it. You can send me an email. I'll be super happy to help you with that. And I'd be happy to have your questions.
Let's thank the speaker again. Thank you for bringing us on schedule.
Cool, thanks for the great talk. One just idea I've had, because I work on ASAN, is I was just wondering if you tried actually inlining the code that checks whether or not something is on the stack, whether you've tried writing your instrumentation path so it actually inlines the check so that you never, like most of the time, you never even call your runtime function.
Yeah, right now we're not doing it. We would love to do some of those check inline, but it's not something we're doing currently.
Cool. The second question I had was, so for when you're using the allocators, like what information, metadata are you actually storing for the allocations?
So typically we store information like the time of allocation and deallocation. We also store information like time of first access and last access. So this allows us, for instance, to say, hey, you haven't touched that chunk of memory for a long time, so maybe you should you have some opportunity to release it earlier and save some memory. And also the range of bytes being accessed. So we store the first byte being accessed and the last byte being accessed. And this is how we highlight, okay, you've allocated 100 items in this array, but only used the first 10.
Cool, thanks.
More questions? Who's first?
Thanks. So on Darwin, we have two tools that I noticed you didn't, that I'll talk about briefly and just ask if you've considered using them or something similar for your use case. So the first is malloc stack logging. So instead of instrumenting the program, you change libmalloc to capture a stack trace and report it in a try. The second is the Heap tool, which can scan the address space of the process. And because it can see the ISO pointers and vtables, it can figure out what types are in your heap and then report their sizes. So is that useful to you, or is that not enough? Or just curious what your experience has been.
So the first one, you would intercept every, you replace the allocator, so you intercept every allocations. And this is what typical heap profiler do. You would like the information about how your program uses the memory. That would be the drawback. For the second one, I could not completely understood it, so
So the way the analysis tool works is by walking all of the VM regions in the process and then inspecting bytes. So if it can find something that looks like a vtable pointer or an ISO pointer, it can look up the type info, and then therefore it can attribute the size of the allocation to that type. So you can see how many bytes are allocated for every type in your program.
Okay. So the way we're doing it is we're doing that at compilation, and actually it is something. So what you could do to have the same information in Memoro is to disable completely the instrumentation, but you would still run it. So that way, you would collect the data from each and every allocation point, the type of each and every allocation point, and you would get the same information without the high overhead introduced by instrumenting every load and store. So this is something we actually are already doing with Memoro.
Okay, I have a question about Thread Sanitizer. As far as I know, they somehow solve that they do not instrument variables on the stack. So I was wondering if you could have used their method to gain better performance.
They don't instrument the stack?
And I think, why would you instrument actually thread local variables, and then the stack is something for that. So that's one question. The other question is about X-ray. So they have as far as I know, I'm not an expert in this territory, they have a pretty good instrumentation mechanism which can be really performant. And I was wondering if you were thinking about perhaps to use their infrastructure for your instrumentation.
So I'm not aware of how they're doing to remove the stack addresses. The get underlying object, we took the ID from ASAN. This is what ASAN is already doing to remove those accesses. I'm not familiar with what other sanitizers do to remove those stack addresses. The thing is that we are more, like taking ASAN for instance, what they do is like a shadow memory. So they just repeat the operation on the memory on the shadow one. And what we're doing is like accessing the metadata, and this is what is really killing our applications, like accessing the metadata that often from the allocators. And so I think there's not a lot of other sanitizers that use the allocators the same way we do. I'm not familiar with what their other approach is. And you're saying that X-Array is also doing a good job at removing those stack accesses?
I'm not an expert on X-ray at all. What I've just heard that how the way they instrument the different calls is that they inject operations, and you can turn on the instrumentation, and that moment the no operations became real instructions, and this way this can be really performant. That's what I heard.
Okay, this is something I need to look into.
Okay,
Because
you
that
can
sounds
follow
interesting.
offline. I
Yeah.
think.
Let's take it offline.
One
That sounds
quick
interesting.
question. Could you tell us about the supported platforms?
Sorry?
The supported platforms. On which platforms I can run this?
It can run on Linux. We have encountered some problem with macOS right now related to thread local variable. Apparently, this is not something that my computer will compile. But other than that, it's really Mac and Linux right now. And there's nothing against Windows usually, but there shouldn't be a lot of work necessary to make it run on Windows.
Thank you. Let's thank Thierry again.
Thank you.